Welcome everybody to this week's Geotalk. It's great to see you all in the audience. Thank you all for joining us this Thursday afternoon, and welcome to our speaker, Leo. Leo is a freshly minted doctor, so we should all refer to him as Dr. Vonopartis for today. He's just received his PhD award, so congrats, Leo, and thank you for agreeing to give us a Geotalk so soon after completing all that arduous process. We really appreciate it. So Leo is a Wits graduate. He completed his BSc degrees, BSc honors degree, and as I said, a PhD degree here at Wits University. And he's now doing a postdoc through Chimera, but he's also traveled during his undergrad through an exchange student program to James Cook University in Australia. And as you'll hear tonight, Leo is obviously fascinated by granite mineralization or granitic mineralization, but one of his guilty pleasures is meteorites, and he's been working on the geochemistry and petrology of meteorites since his honors degree. So thank you all for joining us, and thank you to John Hancock's for sponsoring these Geotalks, which hopefully we'll get back to having in person towards the end of the year, once we get a few more students vaccinated. So thank you all for joining us, and we're going to hand over to Leo. Leo, I'm going to stop my share and you can share your screen. Great, you can see your screen, Leo, and we can hear you. So over to you, go for it.
Good afternoon, everyone, and thanks, Grant, for that lovely intro. Okay, so, well, granites. They're an interesting group of rocks, not only because they make up most of the crust that we live on, but they're also linked to many types of geological environments and are host to many economically interesting minerals. In this talk, I'm going to speak to you about granites and some of the minerals within them that can be used to help us determine the metallogenic potential of a granite. A brief overview of what will be spoken about is, what is a granite? For those of you who are a little bit fuzzy on your felsic side of the rock spectrum, and what economic value granites have, and then how you can find it. As part of my PhD, I looked at granite mineralogy and whether we can use select minerals to identify mineralized granites. I'll speak about two common components in granites, specifically quartz and their trace elements, and the mineral composition of micas. So firstly, a bit of a granite basics. What is a granite? Well, a granitoid is a generic term for a felsic igneous rock that is composed of quartz, plagioclase, and alkali feldspar. A granite specifically is a plutonic rock that consists of quartz, alkali feldspar, plag, and some other minerals. On a QAPF diagram, granites sit in the left middle section of the upper triangle. These rocks are primarily medium to coarse grained, although aplitic or finer grained granites are also included. They are plutonic, and they have a silicate weight percent between 58 to 78. So how do granites form? Well, generally, granites are accepted to form from the partial melting of pre-existing rocks, be it sedimentary, mafic igneous, continental crust, primarily through the melting of biotite, hornblende, cordierite in the source rock. This melt, or felsic magma, then migrates for as long as rheologically possible, possibly fractionating along the way, before stopping or being trapped to cool and crystallize the granite. So basically, the source of a granite can have many compositions. This introduces a little bit of complexity into the classification of these rocks. This was well summarized by Reed in 1957, who said that there are granites and there are granites, as a reference to the over 20 classification schemes that had popped up by then. As the granite controversy is a whole lecture on its own, I won't be delving into the transfers and nuances of the many classifications. For this research, I've used the alphabet soup classification of granites, S, I, and A type. Yes, this is a contentious topic, but this scheme is the one I've used for this research and is the one that most people will be familiar with. On the face of it, it's pretty simple. S is for sedimentary petrolith, I is for igneous petrolith, and A is for anorogenic. And A-type granites are the granites that I'll be focusing on in this talk, and the granites that I'll be comparing. So what are A-type granites? They are not temporally associated with any mountain building environments, excluding the potential volcano that may come about by this magmatism or volcanism. They're commonly associated with plumes or hotspots, extensional environments, and are not directly linked to an orogenic event like subduction. Examples of A-type granites are Nigerian ring complexes, Namibian ring complexes, Yellowstone in the USA, and the Bushveld granites. They are characteristically iron-rich, and their mineralogical assemblages reflect this. They have iron-rich mafic silicates like anite, ferrohedingberite, and phaelite. They have alkali-rich mafic silicates such as agerine, aphitinite, riebeckite, and pathitic alkali feldspars. They're also associated with high field strength elements and rare earth elements, which consequently is an attribute that makes them economically interesting. And if this doesn't sell you, they're also the only known type of granites that are found on other rocky planetary bodies. Although they are not the most abundant granitoids on Earth, and they don't form enormous mineral deposits, they do host various commodities of interest at the moment, such as tin and tungsten for touchscreens, lithium, lead, zinc for batteries, molybdenum for steel production, fluorine for nice smiles, uranium, thorium for energy, and niobium, tantalum, and rare earth elements for all the green energy solutions that are coming about. One way of determining the mineralization potential of a lithology has been by using indicator minerals. This has been successfully done in many geological contexts, ranging from diamonds to porphyry coppers through a variety of minerals. However, there hasn't been much emphasis on indicator minerals for endogranitic tin tungsten mineralization, so mineralization within granites. So I looked at two common granitic components, namely quartz and mica, from granites of the Bushveld igneous complex to see if we can use them. Although commonly overlooked, a significant portion of the Bushveld is actually felsic. It is in no way comparable to the ore output of the Rustenburg layered suite, but historically was a major tin producer, and it is still one of the largest fluorspar producers in the world. The Laboa granite suite has 6 tin fields and various types of polymetallic mineralization. Here, in the northern limb, is the Zaaiplaats Tin Mine, the little star, which hosts various types of endogranitic tin mineralization and was the focus of my PhD thesis. A little bit of history on the tin mine. Tin was first discovered there in the early 1900s, initially on the farm of Groenfontein, on the lower part here, and then Zaaiplaats in the top part. Cassiterite was the ore mineral that they were mining there, and it was successfully mined until the collapse of the stock market in the 80s. resulting in the closure of the tin mines and the halting of tin production in South Africa. Cassiterite mineralization is found in three primary styles in this tin mine: low-grade disseminated cassiterite, shown here in the green, high-grade large hydrothermal pipes, and large lenticular ore bodies, granitic ore bodies, which run parallel to the roof of the intrusion. Cassiterite is primarily hosted in the Bobbejaankop and Lees granites. Basic petrography of these granites is, let's start with the Nebo. So the Nebo granite, shown in gray here, is a coarse-grained leucogranite, which is composed of quartz, alkali feldspar, biotite, and hornblende. It's unmineralized and grades from a hornblende-bearing granite at its base to a biotite-bearing granite at its roof, here in the Zaaiplaats area. The Bobbejaankop granite, which is in orange, is a coarse to medium-grained granite, characteristically red, pinkish red, composed of quartz, alkali feldspar, biotite chlorite, and fluorite, and is partially mineralized. The Lees granite, which forms the roof of the intrusion and the contact between the overlying Rashub granifiers, is fine-grained, slightly granophyric, has a similar mineralogy to that of Bobbejaankop, and is mineralized. The formation of the Zaaiplaats tin granites has been debated for a while, and many hypotheses were proposed. Some suggest that the Lees granite is a chilled margin or an entirely separate intrusion. However, through my research, I propose that a model that builds on the previous fractionation and hydrothermal interpretations of the system. These granites are a consequence of sequential fractionation and crystallization, which results in the accumulation of magmatic hydrothermal fluids in the granite cupola. These fluids saturated the upper facies of the granite, resulting in semicrystalline to subsolidus alteration of the roof facies. Concentration of these fluids resulted in the development of zones of disseminated cassiterite. Channelization of these fluids, as the degree of crystallization of the magma increased, allowed the formation of swarms of large hydrothermal pipes that radiated up from the Bobbejaankop into the overlying Lees granite, terminating before the roof contact. A little bit of a unique vantage point on the northern limb of the bushveld. Here's a map of the northern limb on the top right, and a panoramic image taken from Zaaiplaats Hill. This photo shows a cross-section of the entire northern limb, from the Archean granites shown here on the right, on this side, through the Rustenburg layered suite, into the Nebo, Bobbejaankop, and Lees granites, as you see here, of the Leboa granite suite, and the overlying Rashub granifiers, which I think is pretty cool. So now we're vaguely familiar with the geology of these granites, but what can the minerals show us? We're looking at the general granite petrography. It's made of quartz, feldspar, micas, hornblende, and some accessory minerals. So this is an example of the Nebo granite. Let's look at one of the most significant and characteristic minerals of a granite. It's quartz. Instead of using minerals that are not always present and difficult to analyze, quartz is ubiquitous and has a simple composition. It's pretty easy to identify, as you can see. It forms in both magmatic and hydrothermal systems, allowing us to record the transition from magmatic into hydrothermal. So quartz is pretty simple. It's silica dioxide. Although the composition is simple, these minerals show an appreciable structural and chemical complexity. Due to the small size and the charge of silicon, few elements can directly substitute in this SiO2 tetrahedron, shown here. However, various ions with some coupled substitution can, shown here with the lithium and aluminium. There are two main types of quartz, alpha quartz and beta quartz. Low temperature alpha quartz crystallizes in the final stages of evolution and is a common component in evolved granites, granodiorites, rhyolites, and pegmatites. High temperature beta quartz, other varieties of high temperature quartz polymorphs, are transient species. The transition from beta quartz to alpha quartz at around 573 degrees Celsius involves a minor rotation of the SiO4 tetrahedra during cooling, changing the hexagonal structure of the quartz crystal into a trigonal trapezoidal structure. Those of you who are mathematically inclined may have noticed that this doesn't add up to 100. That's because the interesting parts of the quartz for this investigation lies in the trace elements. Trace elements in quartz provide not only the only compositional variability in an otherwise pretty homogeneous mineral. The incorporation of various trace elements into silica is influenced by the temperature and composition of the magmatic hydrothermal fluids or the magma itself. Aluminium is suggested in igneous quartz to increase with an increase in evolution, the acidity of the fluid, and the aluminium saturation. Titanium is directly correlated with temperature and will decrease with a decrease in temperature. Germanium is principally controlled by its presence in the crystallizing environment, and at lower temperatures and increasingly hydrothermal conditions, GE will substitute preferentially for silica than aluminium. Lithium is commonly used to charge balance, as we've seen before, for aluminium, and in purely magmatic quartz, aluminium and lithium will have a 1-to-1 ratio. Many other elements can be analyzed, detected in quartz, but they are primarily hosted in inclusions and not structurally incorporated. And this can provide insight into the composition of the surrounding fluids or magma. Using the laser ablation facilities at Wits, quartz was analyzed from all the granitic lithologies at Zaaiplaats. I sampled them from the Nebo at the base and increasing in height, stratigraphic height if you would, from the Nebo into the Bobbejaankop and into the Lies. These were taken from both core and in situ granite sampling, and for good measure, we took a pipe as well. The cathodoluminescence of quartz proved quite informative on its own. It revealed an increase in hydrothermal textures from the Nebo to Bobbejaankop to the Lies and then the pipes. Essentially, the Nebo quartz was pretty magmatic, had magmatic Cl signatures. The Bobbejaankop quartz had a core of magmatic quartz similar to that of the Nebo, but later precipitations of hydrothermal quartz. The Lies, although had some magmatic quartz, was predominantly hydrothermal, and the pipe was completely hydrothermal quartz and looked completely different to the granitic quartzes. Here's a Cl image of the Nebo quartz, which you can see is pretty homogeneous, very little zonation. The Bobbejaankop quartz has a core of magmatic quartz similar to that of the Nebo, but a rim going around the edge of hydrothermal quartz. And these are what most of the larger coarse-grained quartz look like. But a lot of the finer-grained quartzes were hydrothermal and were a lot more zoned. The Lies quartz although it did show some magmatic quartz, had a lot more zonation and a lot more hydrothermal textures. But majority of the least quartz looked like this, distinctly more hydrothermal. The quartz from the pipes were completely different. They were very coarse-grained, euhedral, doubly terminating, and if you remember, they look like alpha quartz with a trigonal structure. This indicates a distinctly low temperature hydrothermal regime. So what were the geochemical variations between these zonations? These are some traverses across the quartz grains within each lithology. Only the structural elements, aluminium, germanium, and titanium, were looked at in these traverses, and tin was included because it was the economic element of this area. So in the Nebo, you can see that it's pretty homogeneous throughout the quartz, regardless that there's a slight change in CL luminescence of the edge. The Bobyankop shows the core, this lighter part, to be quite similar to that of the Nebo. And the rim, which is shown to be different, shows an inverse abundance of titanium and aluminium compared to the Nebo granite. This inversion was carried over into the least granite quartz in the initial first two ablation sites. And in the later zonations of the least granite, the changes became more pronounced, where the pipe quartz looks completely distinct. Once you overlay all of these traverses, a clearer picture starts to be revealed. The Nebo quartz is similar to that of the early Bobyankop quartz and are shown to be magmatic. This represents the first stage of the system. The rim of the Bobyankop quartz shows a reversal of the titanium and aluminium with a slight increase in germanium. This is carried through into the early stages of the least quartz and represents the second stage of this section here, the second stage with an increasing hydrothermal signature of the system. The outer half of the least granite, these final red ones here, shows a distinct change in the physiochemical conditions of the system. There's a distinct drop in titanium, an increase in aluminium and germanium, and a slight increase in tin. This shows that the final quartz generations of the least formed in a low temperature hydrothermal system with an increase in acidity. The pipe quartz are completely different and are homogeneous. They have a very high aluminium, very low titanium, and high germanium, indicating a low temperature, acidic, hydrothermal fluid environment. The importance of fractionation in the development of late-stage magmatic hydrothermal fluids is not novel. The link between the degree of magmatic fractionation and the development of mineralization is evident across many granitic systems. Here, illustrating that the more fractionated Lies in the red triangles and Bobyankop in the blue triangles, more fractionated lithologies, are mineralized than the less fractionated Nebo granite, which are here in the black circles. The Lies and Bobyankop have a lower zirconium over hafnium ratio, which is a robust proxy for granitic fractionation. The lower the ratio, the greater the granitic fractionation. So quartz itself can be used as a proxy for fractionation in felsic systems. But more importantly, they hint to the potential to identify a point of fluid saturation within a granitic system. Metals such as tin are concentrated through the accumulation of magmatic hydrothermal fluids. The utility of identifying the point of fluid saturation in a granite shows the potential to identify the facies that are more likely to be, or better candidates to have endogranitic hydrothermal mineralization. The gradual evolution of the quartz, shown in the top section of this diagram here, the bottom section of the diagram here, infers a magmatically controlled fractionation of the quartz. The lower section over here and the higher top right section over here is more scattered and indicates a more erratic and hydrothermally controlled evolution of the quartz, therefore distinguishing between magmatic and fluid saturation. So the Lies and Bobionkop are more likely to have fluid saturation signature and more likely to be mineralized, which is the case. The pipes, which are extremely fractionated and plot right at the bottom of this diagram here, are shown would be the best candidates for mineralization. And in the case of Zaaiplaats, ran grades of up to 80% cassiterite. So let's look at another component of the granite. It's not as abundant as quartz, but it too being associated with both magmatic and hydrothermal processes, the micas. Micas are a common component in granites. They are both magmatic and hydrothermal and are common alteration products, which are associated with mineralization. Even before late-stage alteration, micas are common alteration products of other silicates, such as hornblende. They host volatiles, such as chlorine and fluorine, and some metals, such as tin. Micas have a slightly more sophisticated mineral chemistry than that of quartz, and are capable of extensive trace element incorporation. However, the major element compositions of these micas proved incredibly insightful into the metallogenic potential of fluid evolution in the granite. Very simply, micas are separated into two types, trioctahedral and dioctahedral micas, based on their M site occupancy. Typically, your trioctahedral micas are your magmatic micas, part of igneous and metamorphic assemblages for both mafic and felsic rocks. And dioctahedral micas, which in granites and some other lithologies are usually associated with hydrothermal fluids, such as muscovite, which is a product of granicization, which is linked to mineralization. The cationic substitution of micas allows a very large variety of mineral species and a very wide physiochemical range of stability. Like quartz, this provides an insight into the evolution of a granite from its magmatic beginning to hydrothermal and possibly mineralized conclusion. So micas are a common component of A-type granites, are present in both mineralized and unmineralized systems, occur in both magmatic and hydrothermal regimes. So can their chemistries reveal anything about metallogenic potential of a granite? Does the wide range in stability and compositional plasticity lend itself to record key metallogenic information? To investigate this, I compared the mica and to some extent chlorite of a mineralized A-type system, the Leboa granite suite at Zaaiplaats, to an unmineralized A-type system, the Gaborone granite suite from Botswana. So now we are able to distinguish which lithology in our granitic system is the most evolved using quartz and more likely to be mineralized. So let's take a broader look at these granites now. Part of my thesis entailed comparing the mineralized granites of the Laboa granite suite to that of the unmineralized Gaborone granite suite, because these granites show some congruencies. For instance, they're both A-type granites. They're both on the carp fault craton. Ages are not too close together, but not too far apart. The felsic components of both of these igneous complexes formed from a sequence of evolving granites. They both have late-stage hydrothermal alteration, although the one is distinctly unmineralized, where the other one is very mineralized. A little bit of background on the Gaborone granite suite. It is a structurally controlled mushroom-shaped intrusion in Botswana. It grades concentrically from the core of the intrusion, the Thamaga granite in this light pink, to the main phase of the Kale granite in a bit of a darker pink, outwards to the marginal phase, which is this red, which is the peripheral phase of the intrusion and the contact between the granites and the overlying Kanye volcanic group. The central Thamaga granite is a coarse-grained Rapakivi granite composed of quartz, alkali feldspar, plage biotite, and hornblende, where the surrounding main phase is a coarse to medium-grained leucogranite with a mineralogy similar to that of the Nebo, and grades into a slightly more redder granite, similar to that of the Bobbejaankop. The marginal phase is fine-grained, slightly granophyric, and quite similar to that of the Lies. In terms of whole rock geochemistry, as you can see, these granites are not very different. In terms of rare earths and trace elements, apart from a slight heavy rare earth element enrichment and more pronounced europium anomaly in the Laboa granite suite, and a little bit of a tin enrichment, uranium thorium enrichment, and titanium depletion in the Laboa granite suite, they are quite similar. Both the suites are meta to periluminous, Faroan within plate granites, fractionated, and A2 A-type granites. So generally, there isn't much whole rock geochemical distinction between these granites. So what do the micas look like? Well, the micas from the Gaborone and the Laboa granite suite. So the Thamaga granite from the Gaborone granite suite has biotites with very minor chloratization, where the Nebo granite from the Laboa granite suite also has biotites and minor chloratization. The main phase of the Gaborone and Bobbejaankop of the Laboa are also similar. They both have biotites. They are strongly chloratized with minor glycinization. They slightly differ in the peripheral phases. The marginal phase is mainly chloratized with very minor glycinization, whereas the Lies granite is chloratized but has major glycinization. When the mica compositions are plotted onto the Tischendorf mica classification diagram, a few things are immediately apparent. The trioctahedral micas of the Nebo granite are more Fe rich than the trioctahedral micas of the Gaborone granite suite. There is a progression from anite to Fe biotite within the Gaborone granite suite, with very little variation in the Nebo. And there are dioctahedral micas, a lot of dioctahedral micas from the Laboa granite suite, with very little in the Gaborone granite suite. They're primarily trioctahedral. When comparing these micas to other mica compositions from mineralized and mineralized A-type granites from around the world, a bit of a clearer picture is produced. The comparison of the Laboa and Gaborone granite suites to other micas from mineralized and unmineralized systems, such as Nigeria, Pikes Peak, the Appalachians, reveals something telling. You can see three clusters or trends: a magnesium evolution of micas, an Fe-Li evolution of micas, and your cluster of dioctahedral micas. And when taking into consideration the mineralization associated with these mica compositions, you notice that the magnesium trend are associated with unmineralized A-type granites. Mineralized A-type granites follow the iron lithium trend of mica evolution. And as you would expect, Grison-related mineralization is associated with all the dioctahedral micas. When classifying the mica compositions according to the style of mineralization in which they are hosted in the granite, develop this diagram, which distinguishes the different styles of granitic mineralization based on mica compositions. And this shows the potential to evaluate the metallogenic potential of an A-type granite system. This Tischendorf diagram shows an interesting trend in the mica evolution and may suggest the possibility of trioctahedral micas to become dioctahedral micas purely through the evolution of the system. However, it was shown by Monnier and Robert in 1986 that there is a compositional and structural barrier that prevents trioctahedral micas from directly changing into dioctahedral micas. The formation of dioctahedral micas and gracinization is key to the precipitation of metals from a late-stage fluid. Although gracinization is a key mechanism, in the formation of these types of mineralization, it seems that it requires an intermediary step to facilitate this transition. The chloratization of trioctahedral micas seems to be a prerequisite for gracinization. In evolution of the system, a common feature is an increasing chloratization of the micas towards the roof facies. So here the nebo becomes increasingly chloratized to the end members of chlorite. When analyzing mica, it is unavoidable that you'll analyze chlorite. So to distinguish between chlorite and mica, I used 5.5 weight percent potassium oxide as a halfway point, if you would. As chloratization involves the removal of potassium from the intercationic site of mica, of the sheet silicate. This diagram illustrates the process of chloratization towards the right, and then the later gracinization or muscovatization of micas of chlorite from the right towards the left. And you can see that there is chloratization associated with the Gaborone granite suite and very little gracinization, as opposed to the Laboa granite suite. One of the key insights on mineralization drawn from the compositions of these micas is the importance of chlorine and the iron or magnesium dominant evolution of these micas. The high chlorine content of the nebo micas indicate that there was an abundance of chlorine in the early magmatic system, which is key for the complexation and transportation of metals. This is lacking in the Gaborone granite suite. The chloratization of these micas would have liberated chlorite from the anite, dramatically increasing the metal complexation potential of the circulating fluids. Another factor is the preferential sequestration of fluorine by magnesium-dominant trioctahedral micas, such as in the Gaborone granite suite. The later development of magnesium-rich micas from the thermogranite to the main phase removes fluorine from the hydrothermal system, thus reducing the potential acidity and ability for the late-stage hydrothermal fluids to become grassnizing. This ultimately hindered the grassnization potential and the development of a suitable magmatic hydrothermal fluid to form late-stage mineralization. So a little flow diagram to illustrate the key factors which result in late-stage mineralization of an A-type. The formation and evolution of Fe-rich micas allows an increase in fluorine in the fluid as it is not sequestered. An increase in acidity allows an increase in complexation. Another aspect of iron-rich trioctahedral micas is that they tend to sequester metals such as tin. So the chloratization of these nebo micas would have released chlorine and tin into the fluid, facilitating complexation and transportation. They would not sequester fluorine as the granites evolved, therefore increasing the grassnization potential of this fluid. This is seen by the Bobbionkop and these micas being dioctahedral, having high iron, low chlorine, as most of it is in the fluid complex, high fluorine because there's an increase in fluorine in the late stage system, and associated with mineralization because grassnization induces the precipitation of metals such as tin as SNO2. In contrast, the Gaborone granites illustrate an unfavorable evolution of A-type granites. No chlorine to transport and accumulate metals. Fluorine was sequestered by more magnesium-rich micas, therefore reducing the acidity of the hydrothermal fluid and lowering the likelihood of late-stage grassnization. So the chloratization of these micas and the resulting low fluorine fluid with no chlorine reduces the complexation potential and makes the fluid non-grassnizing. And this is seen as the late stage granites of the system are predominantly trioctahedral with their micas and are chloratized with very little grassnization and dioctahedral mica formation. They have high magnesium content, low chlorine, very high fluorine, and are unmineralized. Thus, the metallogenic potential of a granite system can be inferred from micas. For an economically favorable system, you would like to see an Fe-Li mica evolution trend, early presence of chlorine, an indication that the late stage fluids were acidic, chloratization before grassnization. So in conclusion, the quartz can tell us the most fractionated lithologies in the system and the point at which fluid saturation happened. While micas provide a criteria to evaluate the metallogenic potential and describe the evolution and likelihood for any late-stage magmatic hydrothermal fluid to develop mineralization. Thank you.
Leo, thank you very much. That was a beautifully illustrated and very, very interesting talk. So thank you. Much appreciated. Do we have, leave your slides up, Leo, just in case anyone has any questions for you. Do we have any questions from the audience? Just to remind you, there's several ways that you can ask the questions. You can raise your hand, or you can ask a question through the Q&A function. So I believe I see a hand raised from Sharad. So Sharad, go for it. You're able to talk. You just need to unmute.
Okay, can you hear me now?
Yep.
Yeah.
Yeah, okay. Thanks for a great talk, Leonidas, and congratulations on your PhD. You showed in one of your diagrams the evolution from a magmatic to a hydrothermal system in quartz. The titanium content is very high in magmatic system, and then as you get into a hydrothermal system, the titanium content decreases, right, until you found in your hydrothermal pipes the least amount of titanium. So from an exploration point of view, if one is looking for a mineralized granitic system, the first thing to look for is something that indicates low titanium. Now, one of the easiest things to recognize in granites, in hand specimen, is cloudy quartz, which gives a bluish color. And that is usually due to titanium that is present as little rutile needles in quartz. And that's a high temperature magmatic texture. So you can just look at a hand specimen of a granite and see if you've got bluish quartz in there, it's got low metallogenic potential. Would you agree with that statement?
That's correct. In the main phase of the color granite of the Gaborone granite suite, you have characteristically blue quartz, which is the result of rutile needles in the quartz. So yes, these granites do show that, and you can use that as an indication of high titanium in the quartz. But for lower temperature quartz, I don't think that would be possible. But yes, you're right.
Okay, thanks.
All right, and then Leo, I'm not sure if you can see the Q&A, but there's a question from Lou. And the first part of the question is, why no titanium in quartz thermometry? And the second part is, can aluminium be used as a geothermometer?
So to answer the first part of the question, the reason I didn't use titanium in quartz geothermometry is because I didn't find any cogenetic or magmatic rutile in the system. And I didn't, without present rutile, you have to calculate your titanium saturation of your granite. By doing that, you would need to do probe work on ilmenite or other phases that are titanium sensitive. And after speaking to Axel Muller, there is a little bit of debate on the accuracy of titanium in quartz, and I thought that without having something solid such as rutile, which will indicate titanium saturation in my granite, it wouldn't be very accurate, so I decided against it. The second part of the question is aluminium as a geothermometer. The mechanisms that control aluminium substitution in quartz are quite complicated because it involves the coupled substitution of things such as lithium and phosphorus and a couple of other things, which is quite well covered in a couple of papers by Axel Muller from like 2000, 2003, but it is commonly accepted at the moment that the increase in aluminium in quartz is linked to an aluminium saturation index. And I'm not too sure whether or not that is temperature sensitive. So I'm not sure.
Okay, thanks, Leo. That's great. Judith, I saw your hand pop up briefly. I'm not sure if you still have a question, but I'll allow you to talk. You just need to unmute yourself.
No, I was going to comment on Sharon's question, but Leo gave a good answer. Thanks.
Good. All right. Do we have any other questions from the audience? Don't see any hands popping up right now. So if there aren't any further questions, then Leo, I'm just going to thank you once again for that great talk. Congratulations on your PhD once again. And yeah, thank you very much. And hopefully some of this will be published soon.
Thank you.
Look forward to it. Keep up the great work. And thank you all for joining us. We really appreciate you coming to the Geotalks, which hopefully will be in person again soon. And thank you to John Hancock's. And just to let you know, we are going on, several of us of the staff are going on field school for 2 weeks from next week. So we don't have any Geotalks planned, unless anyone has a burning topic which they'd like to present on. We'll take a 2-week break, and then you'll see us back again for the remainder of the year in the first week of October. Thanks, everyone, and have a wonderful evening. Cheers.